Okay, so we'll now turn our attention to situations where the angular acceleration is a constant. And if we recall from previous videos, angular velocity was defined as the time rate of change of angular position, and angular acceleration was defined as the time rate of change of angular velocity. And while these are not the same physical variables as translational position, translational velocity, and translational acceleration, if we remember that velocity was defined as the time rate of change of position and acceleration was defined as the time rate of change of velocity, the important thing here is that these quantities have the same mathematical relationship with each other. And so if we, just like before when we came up with the gang of four for translational kinematics, where we were assuming that translational acceleration was a constant, if we assume that angular acceleration is a constant, we'll end up getting yet another gang of four, this one relating rotational variables. So we have a missing theta, as in the equation, which means missing angular position. So omega final equals omega initial plus alpha delta t. A missing final angular velocity, a missing angular acceleration, and again, a missing time equation. And you pick the equations and you solve them using exactly the same kind of techniques we've done before. So let's go ahead and just work one quick example of that. So let's say that I've got a wheel that's spinning but slowing down to a stop. So let's say that it was initially going at pi over 2 radians per second, and it goes to a stop, so final angular velocity of 0 after 20 seconds has elapsed. So what I want to know is how many revolutions did it make in this braking process. So we're free to choose our initial angular position, so we'll just say it's 0. And so this amounts to asking for the final angular position, but I threw a bit of curveball because we're going to get how many radians it churned through, but we're going to have to turn the radians into revolutions. And we can do that by realizing that every time you make a revolution, you rotate through 2 pi radians. All right, so we're being asked for theta final. We're being given omega initial, omega final, and the time. We are missing the angular acceleration. So that relation is theta final equals theta initial plus 1/2 omega initial plus omega final times the time. So again, I am always opposed to putting in numbers with the exception of 0. But we have 2 zeros here, so let's put them in. The initial angular position we can set to 0, and we were given that the thing eventually coasted down to a stop, so we can set the final angular velocity to 0. So my final angular position, so the angle I churned through, will be 1/2 omega initial delta t. So this is 1/2 times pi over 2 radians per second, and this will be times our 20 seconds. All right. So if we work that through, this is pi over 4. Let's see, the seconds cancel. So we got pi over 4, 20 over 4 is 5. So we went through 5 pi radians. But we were being asked for revolutions. So we remember that one revolution has 2 pi radians. So this will work out. The pi's cancel, you get 5/2 or 2.5 revolutions. And any other problem that you run across, you can treat similarly. Alrighty, so that was a brief one there. In the next set of videos, we will start taking a look at forces. We'll see you over there.